Let's start today by deriving the derivatives of sine and cosine. So we'll start with f of x being sine of x. Do a limit calculation. The definition of the derivative, f prime of x, is the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. That's the definition of the derivative. What does it mean for this function that you do? It means you do the limit as h goes to 0 of sine of x plus h minus sine of x, all divided by h. What do we usually do at this point? We usually try to do some algebra to see if we can't simplify this in some way, some trick perhaps, to cancel the h in the bottom so that in the end we can plug in h equals 0. It's not at all clear what kind of trick might be helpful here. You might wonder, well, maybe I need to get the tangent involved, so maybe I should divide the top and the bottom by cosine of x or cosine of x plus h, and you could try that. Doesn't help much. You could try maybe, I don't know, taking the inverse sine of the top and the bottom. Well, that sounds kind of weird. Maybe I shouldn't do that. Here's what you need to do instead as a first step. It's not the complete answer, but as a first step. When you're dealing with trigonometric equations, and it's really unclear what to do, 90% of the time, some trig identity might be helpful. So you try it and see if it's helpful or not. Maybe it'll be helpful, maybe it won't, but more likely than not, if you pick the right one, it will be helpful. Trigonometric identities are actually pretty amazing, and they can quite often be helpful. And you can look them up in a book, but you can also look them up on Wikipedia, for example, and assume nobody's messed with the Wikipedia page. Trigonometric functions or identities. Trigonometric identities. List of trigonometric identities. That sounds good, although it is a long list. Theoretically, there are infinitely many trigonometric identities that you could write down, infinitely many, and I'm not joking. Of course, there are some are more important than others, like cos squared plus theta plus sine squared theta equals 1. That's a pretty fundamental one. So you're scanning through this. What do we want? Well, we're dealing with cosine of, or sine of x plus h, sine of a sum. Oh, this is starting to look good there. Sine of theta plus pi, but that's a special number, pi. Oh, this is looking better. Sine of alpha plus beta, where alpha and beta are arbitrary angles, is sine alpha cos beta plus cos alpha sine beta. It's called an angle addition formula. It doesn't matter that we're not thinking of x and h as being angles. Whether something's an angle or not is all in how you are applying it. It's a number. Go ahead and apply this first formula right there with alpha equal to x and beta equal to h. So we get the limit as h goes to 0 of sine x cos h plus cos x sine h. That's what this entire thing represents, just this expression right there. Don't forget to subtract off sine of x and then divide by h. Oh, we made it worse. That doesn't look so good. Just double checking. Yeah, I think I did that right. It looks worse. How can this be helpful? Take a breath. Maybe it's still helpful. Keep going, keep trying things like, what could we do with this? Well, you stare at it for a while. Maybe go get a cup of coffee. Come back, stare at it for a while. Maybe go take a nap. Come back, stare at it for a while. And then all of a sudden, the light bulb goes off in your brain and says, hey, these two terms here and here both involve a sine of x as a factor. maybe I should factor it out of those two terms. Whew. Let's see what happens when we do. So if I factor it out of there, I get a cosine of h. And if I factor it out of there, I get a -1. Don't forget, you still got to have that term there. And you say, whoopee, what have I done? It doesn't seem like I've done very much. So you go get some more coffee, stare at it for a while. Then you say to yourself, okay, wait a minute. Okay, x is a constant when I'm doing this calculation. H is the variable, right? That's the way you want to think. X is fixed. H is what's going to 0. So anything involving an x, I could think of it as a constant. It could be factored out in front of the limit. At least if I had it as a product without the sum there. But hey, wait a minute. I could also, I could break this fraction up into pieces. I'm sort of I'm undoing fraction addition. I could write this. Because if we were given this expression right there, we could add the fractions because they already have a common denominator. And in each of those cases, I've got a sine of x there and a cosine of x there that effectively with the limit are constants. And I also know the limit of a sum is the sum of the limits. I'm doing lots of steps here, but it's worthwhile. Let me write this. I can write limit as h goes to 0, sine of x times the fraction cosine of h minus 1 over h, plus the limit as h goes to 0 of cosine of x times sine of h over h. And yeah, now factor out the terms that involve just x. Factor those out. What will that give me? Sine of x times the limit as h goes to 0 of cosine of h minus 1 divided by h plus cosine of x times the limit as h goes to 0 of sine of h divided by h. Crazy, huh? This is all valid math. Reasons, that's the definition of the derivative. That's just substituting into the function. That's a trigonometric identity. This is just a bit of algebra factoring. This is also just a bit of algebra breaking apart the fraction into two pieces with the same denominator. This is also algebra plus a limit property, that one right there. The limit of a sum is the sum of the limits. The limit of a sum is the sum of the limits. It's a property in chapter 1. You can look it up. And this is another property of limits. When you're doing this, you're thinking of x as fixed. Now, in the end, after you're done, then you think of x as a variable. Again, whether something's a variable or a constant, it's all in your head. It's all in how you're thinking about it. But it matters. We want to think of x as constant here and h as the variable. So with respect to the limit, I can factor this constant out and that constant out. And now remember what the answer is supposed to be. I mean, you wouldn't know this unless I told you, unless you looked it up. The derivative of sine is supposed to be cosine. I got the derivative to be sine of x times that number, that limit is some number, plus cosine of x times that number. The final answer is supposed to be cosine. This number must be 0 and this number must be 1. Is that true? It is, yeah. Let's see some graphical evidence of it. So I'm going to graph cosine of h, but I've got to type an x in my calculator, minus 1 divided by h, and sine of h divided by h. These two functions, pretending the x is an h, correspond to the two things I'm taking the limit of as h goes to 0. In the calculator, the x is playing the role of the h. So I want to graph these near zero and see if I can tell if they got a limit or not. Technically speaking, you might say, well, wouldn't they have vertical asymptotes because you're dividing by zero? Not necessarily, because the top is going to zero as well as h goes to zero. Sine of h goes to zero as h goes to zero. And cosine of h goes to 1 as h goes to 0, and 1 minus 1 is 0. These don't necessarily have vertical asymptotes in their graphs. Pick a window near 0. Like this, and maybe the y needs to be bigger. Let's try negative 1.5 to positive 1.5. X is going between negative 0.5 and positive 0.5, y between negative 1.5 and positive 1.5. Let's see what we see. Here's cosine of x, h minus 1 over h. Looks like it goes to the origin. There's sine of h over h. Looks like maybe it goes through 1. We could trace. Sine of x over x. You can see those numbers. X is close to 0, y is close to 1. With the other one, x is close to 0, y is close to 0. Technically speaking, there's holes in the graph. There's points missing. These are removable discontinuities. Technically speaking, these functions are undefined when h is 0, but the limit exists. Functions with holes in their graphs are actually important. They seem like minor curiosities, but they are important. They come up right now. And these limits do exist. This limit is 0, and this limit is 1. And so the answer is 0 plus 1, cosine of x times 1, which is cosine of x. So the derivative of sine is cosine, proved with the trigonometric identity, and, well, graphical evidence. Technically, we haven't really proved that this limit is 0, and we haven't really proved that this limit is 1. That is true, and it can be proved. A couple different ways these limits can be proved. One is geometrically, by thinking about the unit circle definitions of cosine and sine, though that is a geometric argument, which many people like, but some people don't like. There are symbolic arguments you can give as well, though technically it's a little bit of a circular argument because the symbolic arguments require what are called infinite series representations of cosine and sine, which really require calculus to derive in the first place. So that's a bit of a conundrum, but it is true. That limit is 0 and this limit is 1. I'm not going to go through those arguments, okay? They're beyond the scope of this course. So the derivative of sine is cosine. What about the derivative of cosine? We saw, I told you that it's negative sine. F of x is cosine of x. F prime of x is negative sine of x. Pun, well, not really intended. Negative sine is not a negative sine, like SIGN is a negative sine function. Do I have to go through all this again? I could, but I don't have to, actually. How could I avoid doing that? I actually could use another trigonometric identity and the fact that I just derived to do it. Think about the way cosine and sine are related to each other. They're horizontal translations of each other. Cosine of x starts up at 1 when x is 0 and goes down. If I take the graph of the sine function, which starts at 0 and goes up, and shift it to the left by pi over 2 units, I get the cosine function. The cosine function is the same as sine of the input minus pi over 2. They're the exact same thing. That's a trigonometric identity. It's not an equation. By the way, identities are equations that are true always for all numbers in the domain. They're not equations to solve. They're equations that are always true. That's the difference between an ordinary equation that you solve and an identity. So then f prime of x should be, it's the derivative of cosine, which will be the derivative of this, because they're the same function. But the derivative of that, by the chain rule, the outside function is sine, the inside function is x minus pi over 2. So this is practice with the chain rule. Take the derivative of the outside, the sine function, to get the cosine function, plug in the inside function, x minus pi over 2, then multiply times the derivative of the inside function, which is just 1. The derivative of x minus pi over 2 is 1. It's a linear function with a slope of 1. So the derivative of cosine is cosine of x minus pi over 2. If you take the graph of cosine, starting up at the peak when x is 0, and shift it to the left by pi over 2, you'll get a graph that starts at 0 and goes down right away. You'll get the sine function, or the opposite of the sine function, negative sine x. Done. That's all you have to do. I'm relying on trigonometric identities there, different ones than I relied on with the first problem. Again, for emphasis, it is important that the input for the variable be in radians, to think of it this way, to get the right answers. That's if you're thinking of the variable as being an angle, at least. If you're not thinking of the variable as being an angle, we define the cosine and sine to be whatever you would get if you thought of the variable as being an angle, as long as you measured it in radians. That was the unit circle definition. That allowed us to take the graphs of cosine and sine. That might sound confusing, but that really is what's going on. Effectively, it's in your calculator, you got to make sure you're in radian mode. Otherwise, that limit in particular is not 1 if the input's not in radians. And so the answer is different. I'll let you see if you can figure out what it is, perhaps.